chemical equilibrium. To understand this concept, we need to first understand that all chemical reactions can go in both directions, in the forward direction and in the reverse reaction. Chemical equilibrium is the condition at which the forward reaction and the reverse reactions are occurring at exactly the same rate. So we'll first go over the dynamic nature of chemical equilibrium, or in other words, the reaction can go both ways. At equilibrium, the reaction has not stopped. Rather, it's going on in both directions at the same rate. Then we'll go over the expression of different equilibrium constants and how to interconvert between Kc and Kp. Next, we then will talk about how to manipulate equilibrium constants with different reactions but related reactions. Then we'll go on and talk about equilibrium constants and reaction quotients and use the Q reaction quotients and the K equilibrium constant relationship and talk about how to determine if the reaction is at equilibrium or not. We'll also talk about the so-called heterogeneous equilibria and talk about how to express the equilibrium constant for those type of reactions. Then we will talk about the Châtelier's principle, which tells us if a reaction at equilibrium is perturbed by changing of the condition, to which direction the reaction will shift to re-establish the equilibrium. Then lastly, we'll talk about some calculations based on the equilibrium constant K. So let's start the first topic, which is the dynamic nature for chemical equilibrium. When a chemical reaction reaches chemical equilibrium, one key feature is the rate for the forward reaction and the rate for the reverse reaction are exactly the same. But I want to emphasize one thing. It's not the rate constants. It's the rates but not rate constants. Rate constants most likely is different. Not rate constants, but rates for the forward reaction and reverse reactions are exactly the same. Let's look at one specific example. Consider this industrial process for making hydrogen gas. In the first step, methane and water react to form carbon monoxide CO and hydrogen H2. In the second step, which is shown on this slide, carbon monoxide produced in the first step reacts with more water to form hydrogen and carbon dioxide instead. If we start with an equal amount of water and CO, as you see over here, the forward reaction will proceed rapidly in the very beginning because the CO and the water are converted to hydrogen and carbon monoxide. As you can see in this diagram, as the concentrations of carbon monoxide or water decreases in this reaction coordinate, the concentrations of the products, carbon dioxide or hydrogen, they actually increase. At a certain point of time, you will notice the concentrations for the products stays constant, as well as the concentrations for the reactants. Once the concentrations of the reactants and products do not have a net change, we know the reaction is at equilibrium. This is one way to determine if the reaction is at equilibrium or not. We can also look at reaction rates. For the forward reaction, the reaction starts with the high rate, but it's going to drop because the concentrations of the reactants will decrease as the reaction goes on. At the same time, the rates for the reverse reaction will increase because the concentrations of the products increase. At a certain point of time, the rates for the forward reaction and for the reverse reaction will be exactly the same. At this stage, we know the reaction has reached the equilibrium. As you can see in this shaded area, the rates for the forward reaction and the reverse reaction are exactly the same. So we know the reaction equilibrium is achieved. Let's look at another reaction. This reaction is the reaction that involves nitrogen dioxide, NO2, the gas responsible for the brown haze associated with photochemical smog. This molecule will establish an equilibrium in the reverse reaction with N2O4, dinitrogen tetroxide. Chemists know from experimental data that the rate laws for the forward and reverse reactions are the Kf times this concentration, and for the reverse reaction you have the rates like this. But I'm going to add a point over here. These rate laws must be experimentally determined. You cannot read this reaction and have that rate law. If you have already learned the chemical kinetics chapter, you will know this already. If you have not, just take this to your heart first. All the rate laws must be experimentally determined. So these two laws over here, they are derived from the experimental data. All right, now let's move on. One key feature, though, is that when this reaction reaches equilibrium, the forward reaction and the reverse reaction will have exactly the same rate. So this rate and the reverse rate will be the same. In other words, we can write an equation as you see over here. Kf times NO2 squared is Kr times concentration of N2O4. All right. If you rearrange this, you will find out the rate constants for the forward reaction divided by the rate constant for the forward reaction divided by that of the reverse reaction will take the form that is exactly the same as the expression of the reaction constant. Okay, reaction equilibrium constant, and this constant we call that equilibrium constant. The phenomenon by which the equilibrium constant expression produces a constant value at a given temperature is called the law of mass action. The ratio of the concentrations or partial pressures of the products over reactants, each raised to a power equal to the chemical coefficient for the substance in the balanced chemical reaction, is called the mass action expression. We will give you specific examples right now. For example, in the same reaction we just studied, the equilibrium constant expression will be seen as over here. The concentration of the products raised to the power of 1, which is not written, that corresponds to the 1 as you see over here. If it's a 2 in the chemical reaction, this power would be raised to the same power. So similarly, this is raised to 1 for CO2 because it corresponds to the chemical coefficient before CO2, which is 1. So at the bottom, it's the same way. All right. Also, pay attention to the phases, which you're going to find out to be very important. Mathematically speaking, we started this reaction and measured the concentrations under equilibrium with different starting conditions. The experiments have proved the equilibrium constant will be exactly the same at the same temperature, no matter which starting concentration combination you have. So that's the basis for the law of mass action. For a generic equation, as you see over here, let's indicate the phases because it's quite important for this chapter. So let's say A exists in gas phase, B as well, and C, D. So the uppercase letters A, B, C, and D, they represent different chemicals. So AB being the reactants and CD products. The lowercase a, b, c, d, they are the chemical coefficients which are used to balance the chemical reaction. So for the equilibrium constant based on concentration, we use a subscript C to represent it's based on concentration. If it's based on partial pressure, we use P as the subscript. When you write this, it's always, when you write the equilibrium constant, it's always the concentrations raised to corresponding power. If it's 1, it's 1. If C is 2, then you write a 2 over here. You always need to raise to the power to the corresponding chemical coefficients. Similarly, for Kp, it's the same, but we use the partial pressures of the gas phases rather than the concentrations. If you recall, in the very beginning, we emphasized a couple of things. First, all reactions are dynamic in nature, which means all reactions will go in both directions, the forward direction and the reverse reaction. Secondly, the equilibrium constant will have either a small or large value, but they will tell you no information about how fast or how slow the reaction goes. Rather, if you have a large equilibrium constant, basically what it tells you is, because what you see previously, because equilibrium constant is based on the products over the reactants. So a larger K just means at equilibrium you have way more products than the reactants and vice versa. So when you look at these three specific examples, the first reaction, you have a really large K equilibrium constant. That just means the reaction favors the formation of the products. But it does not tell you if this reaction is fast or slow. All right, just want to emphasize that. For the second reaction, it's quite the opposite. An extremely small equilibrium constant tells you the reaction favors the reactant or the reaction lies to the far left. It's exactly the same way. All right. Now the third condition, you just have an intermediate magnitude of K. This just tells you the reaction is right in the middle. It favors a little bit the product, but not by too much. If the equilibrium concentrations or partial pressures are given, it's quite straightforward to calculate the equilibrium constant. Given the concentrations at equilibrium. So it tells you that these are at equilibrium already. So if they are at equilibrium, you can simply do the K calculation according to the law of mass action, according to the definition of K. So let's substitute the numbers in. Then you do the calculation. Remember, it's products over reactants, and they are all raised to the corresponding power. You see this number 3, it corresponds to this 3 over here, right? This 2 corresponding to the chemical coefficient here, and 1 which is not written corresponds to this one, right? So substitute the numbers in, you get a small k, which tells you the reaction favors the left side or lies to the left or favors the reactants. We just noticed the equilibrium constant can be expressed in either concentration or partial pressure. So you might be wondering, what are the relationship between Kp and Kc? If you noticed, if we use ideal gas law, PV is nRT for the gas phase. So if you divide by V on both sides, you would have an equation on your right side. Do remember, N is number of moles. Moles divided by V, which is in liter in ideal gas law. So this N over V is actually the concentration. So for example, for substance A, let's say a substance A, all right, then let me rewrite the top one, okay. The P would be N over V is concentration, okay. It's concentration for X, let's say, all right, times RT, okay, PX for anything. So for substance A, it would be concentration A times RT. For substance B, it would be B times RT, okay, and etc. PC, PD. If you substitute this into the representation for Kp, let me write the whole thing. All right. Do remember, Kp equals the Pc raised to C, Pd raised to D, and Pa raised to A times Pb raised to B. So if you substitute Pa over Pb, Pcbt into the Kp expression, you'll find out Kp and Kc have this relationship. Kp is Kc times parenthesis R times T raised to delta N. So what is the delta N over here? Delta N is basically the C plus D minus A plus B. Oh, by the way, if you forget what we are talking about, right? This is for the generic reaction. AA reacting with BB produces CC and DD. Okay, that's all based on this generic reaction. So, one more time. We are able to find out the Kp and Kc relationship. And Kp is Kc times RT, R times T raised to delta N. Let's look at one example. So in this chemical reaction, we ask you to write the equilibrium constant expression, Kp, for the synthesis of NO2 as you see over here. All right, how do you write this? Apparently, Kp would be, it's Kp, so it's based on partial pressure. It's NO2 raised to the chemical coefficient number 4 times the P for water. Remember, that's gas phase. If it's not gas phase, you're not going to be able to include that, okay? And when we talk about heterogeneous equilibrium constant expression, you will notice that over here, everything is expressed in gas phase, okay? All right, for the partial pressure of NH3, it's raised to 4 as well. Now for oxygen, it's raised to 7. So that's exactly what you expect to see. Let's look at another example. In this example, we are asked to calculate Kp for a certain reaction at equilibrium given the Kc. So we do know the Kp-Kc relationship, which you will have to memorize or put on your note card. Okay, Kp equals Kc times RT raised to delta N, and do remember the delta N is actually C plus D minus A plus B. Another thing is, again, over here, of course, you are given this Kc, so this is check, and R is ideal gas constant. It's a gas constant. It's 0. So if you write this, it would be 0.08206 atm liter per mole per K, right? Then this T must be in Kelvin temperature scale, okay? All right. Another thing is, if it's Kp that's given, you want to find out a Kc, it would be easily, you can easily rewrite this thing. It would be Kc equals Kp times RT parenthesis raised to delta N. You should be able to go back and forth with this one. All right. For this specific case, so we can just let's look at this specific case. All right. So you put down the numbers. All right. Temperature converted to Kelvin. All right. Delta N is 1 plus 1 minus the other one. That's why it's 2 minus 1 equals 1. So you substitute the numbers in and do the calculation. Kp equals Kc times R times T in Kelvin raised to delta N. So you have a number 229. And this reaction is slightly greater than number 1. So this just tells you the reaction is favoring the products. Let's quickly summarize this section. K, equilibrium constant, can be expressed in terms of concentrations or in terms of partial pressures. And with this, we have the Kc and Kp, which are related by the equation Kp equals Kc times parenthesis R times T parenthesis raised to delta N. Next, we are going to talk about how to derive the equilibrium constant for an unknown reaction based on the known reaction. We will learn how to manipulate the equilibrium constant in the next section. For example, if you have a specific reaction as what we have discussed over here, the original reaction has a K expression as the products over the reactants, as you see over here. It's raised to the corresponding chemical coefficient. For the reverse reaction, your K will have products over reactants. As you notice, the forward reaction and the reverse reaction, they are inverse related. So if this is reaction 1, this is reaction 2. So if you reverse a reaction, let's call this K1. It's a little bit easier. Okay, so, and here you have K2. So basically what this tells you, if you reverse the reaction, the equilibrium constant is inversed. That's the first relationship. The second one, if you multiply the original reaction by a certain number, all right? For example, let's do this, let's multiply the first one by a different number, okay? So this one, just multiply the reaction by first one by a half, okay? When you do that, reaction 2 will have K2 equals K1 raised to a half, which is the thing that you just multiplied by. So if I multiply reaction by n times, okay, so if it's reaction 1 multiplied by n times, and this gives you reaction 2, okay. So for this, the more generic one would be K2 is K1 raised to n. Let me rewrite, yeah. So K2 is K1 raised to n. So if you multiply an original reaction by n times, the equilibrium constant for the new reaction will be the original raised to n, not this one. No, it's not n times k1. It's k1 raised to n. The second one, no, it's wrong. Okay? All right. We're going to look at another situation. What if you have two reactions to begin with? All right. So let's call that reaction 1 and reaction 2. And you combine it together by canceling out the same terms as you see over here. Then you get a new reaction. You have the corresponding original K expressions. What about the K expression for the third reaction? Yeah, when you write the third reaction, all right, you will notice that eventually rewrite the K expression, all right, which is the K expression you see over here for the third reaction. That's the products, okay? That's the reactant 1. That's another reactant, all right. But you can rearrange this thing, and you notice that if I put an NO2 over the top and another NO2 raised to 2 at the bottom, they can cancel out. But the first term would be exactly the same as K1. Did you notice that? That's your K1. And the second one would be K2. You see? So basically, this just tells you this question mark should be replaced with the multiplied by. So, summarize this. If you have two original reactions and you add it together to make the third reaction, then K3 will be the product of the first and second reaction equilibrium constant. Not this, not this, not K1 plus K2. That's totally wrong. It's K1 times K2. All right. Now let's go back a little bit and review one topic we actually talked about previously, so you can learn a little bit more about this. All right. For example, if you do a reverse reaction, and if we don't study the equilibrium constant, rather we study the delta H1 and we study the delta H2, what's the relationship? Oh, the relationship would be delta H2 is negative delta H1. Why? Because delta H enthalpy change is a state function. It depends on the starting point and the end point. You reverse the reaction, you reverse the starting point and the end point. So the difference between the enthalpy will become the opposite sign. Okay? All right. Now for the second situation, you multiply certain number by n. All right. So what's going to happen for, let's say the first one, this is reaction 1, this is delta H1, and you multiply the whole thing by n. So you would become, let's say this whole thing, if you multiply by n times, let me move back. Then the new reaction 2, all right? New reaction. Number 2, it would become 2n times NO plus n times O2, because each term should be multiplied by n, right? Okay, 2n times NO2. And for this reaction, your delta H2 will be n times delta H1, because you have n times more moles of starting material and your products. Okay, so that's what you see, and we have already learned this in the thermochemistry, in general chemistry 1. Right, compare that. The K relationship versus the delta H relationship. The K relationship versus the delta H relationship. For the combination of two reactions, all right, we noticed for K, it becomes the product of the original two equilibrium constants. If you have delta H1 for reaction 1 and delta H2 for reaction 2, as we learned in Gen Chem 1, delta H3, which is a new reaction, will be delta H1 plus delta H2. Okay? All right. Let's solidify what we just learned using one example. In this example, we are given a balanced chemical reaction and the equilibrium constant Kc, right? And we're asked to calculate the value of Kc for the two other reactions. So two different new reactions, A and B. So apparently, when you need to look at the relationship between the original reaction and the new reaction. So you look at the second reaction. Apparently, it's the reverse reaction of the original one. So for reverse reaction, the new K will become the inverse of the original. Okay. For the second reaction, look at this one. How is this B, reaction B, related to the original reaction as you see over here? You just multiply this original by a half. Then you will see, if you multiply this by a half, what are you going to see? You're going to see a NO2, and that's the first step. All right, step one. Hey, this is the, notice this new reaction in the circle is not exact the same as reaction B, because you need to do another one, which is, look at that, NO2, it's going to be, oh, let me, the reverse reaction. You see that? So when you do this two-step, so basically, let's call this a new reaction. Let's call the first one 1, all right? It's a little bit easier. The second one 2. Of course, you can call that a Ka, Kb, whatever. And this one, I'm going to call that reaction 3, this one, okay? So basically, you look at that. This is K2 is multiplied by a half. So you would know it's K1 raised to a half. Okay? Now, the new reaction is reversed. So in another word, this K3, which is this reaction, okay, K3 would be K2, which is this, inversed. Right? That means 1 over that. Okay? So that's exactly as what you see over here, because Ka is the inverse of the original. Okay? So that's what you see over here. Or K1, that's the K1. I like to use 1, 2, 3 to represent. That's reaction 1, so you can write it as a K1. Okay? All right. So you just substitute numbers in. You'll be able to do this calculation very easily. So in this example, it's based on Ka. But what if you just cross this out? It would be exactly the same. So Kb basically equals Kc a half. See that? That would give you exact the same. Okay, so basically you can look at the stepwise, but if I cross out the intermediate step as you see in step A, you will be able to do that exact the same way, following the procedure I just listed out. Do 2 steps, step 1, and you do step 2. The first step you multiply by a half. The second step you do a reverse reaction. All right, so that's how you can manipulate the equilibrium constant from a known reaction to an unknown. So next we're going to talk about how to judge if one reaction is at equilibrium or not. If it's not equilibrium, to which direction the reaction will is shifting to. All right, so it's 2 things. First, is the reaction at equilibrium or not? If it's not, to which direction will the reaction shift? It's very easy to understand that if the current concentration ratio for the products over that of the reactants raised to the corresponding chemical coefficients. If it's exactly the same as equilibrium constant, then the reaction is at equilibrium. What if it's not? That means it's not equilibrium, right? So for this reason, we're going to define a new term, which is called the reaction quotient. If I write the generic equation for one more time, all right, so let's rewrite this, AA reacting with BB produces CC and DD. Okay, you would define Q. So here's how you define Q. Q is C raised to C, D raised to D, A raised to A, B raised to B. And when you look at the K, K takes exact the same form. So what are we talking about? Really? Exact the same? They take exact the same, that's correct. But do remember, the meaning is totally different. So here, all the concentrations over here, they are the current concentration. Okay, they are the current concentrations. The concentrations in the K expression, they are at equilibrium. So that's the huge difference. Let's summarize it. Reaction quotient and equilibrium constant expressions are exact the same, taken exact the same form, but the meaning is totally different. In the Q reaction quotient expression, the concentrations, or if you have the partial pressures, they are the current concentrations or partial pressures. In contrast, in the equilibrium constant expression, the concentrations or partial pressures, they are at equilibrium. Let's look at one example. In the same example we actually discussed, all right, if Q is smaller than K, what does it mean? If Q is equal to K, what does it mean? If Q is greater than K, what does it mean? Hey, let's go back and look. All right. Q and K, they have exactly the same expressions. Both have the products over the top and the reactants at the bottom. So if Q is smaller than K, do remember one thing before we continue. I'm going to remind you, okay? First, all reactions, they will shift to the reaction that will reach equilibrium. They will shift to the reaction to establish equilibrium. So if Q is smaller than K, this tells you one thing: you have less products than at equilibrium state. You have less products than at equilibrium state, because for both Q and K, you have products over the top, right? So smaller Q than K, that means you have less products than at equilibrium. To reach equilibrium, you will have to shift the product to generate more product. So that's why the reaction will proceed to the right or toward the products. If Q is K or equal to K, of course, the reaction is at equilibrium already. Q greater than K, that means you have more products than you need at equilibrium. So the reaction will proceed to the left side or the reactants, so you can establish equilibrium. All right, let's look at one specific example. So in this example, you are given a chemical reaction and concentrations are given. Remember, these concentrations are the current concentrations because they tells you, hey, that's what we see. That's the concentrations we see over here. Then they ask you, can you tell me if the reaction is at equilibrium or not? If not, to which direction the reaction will shift to. So basically, this is a typical Q and K comparison. If Q is greater than K, you have more products than you need at equilibrium, you'll shift to the left. Otherwise, if Q is smaller than K, you have less product than you need at equilibrium, so you're going to shift to the right side. If Q is K, then you are at equilibrium already. So let's simply do the Q calculation and compare with K. That's exactly what you do. Remember, all these concentrations you see over here, they are current concentrations. They take exact the same form as the K expression, okay, raised to the corresponding power. So you calculate the Q, you find out Q is greater than Kc, which is 5.6. That means you have more products than you need at equilibrium, so the reaction should shift to the left side. All right, so let's summarize the Q and the K relationship for one more time. I know we've been emphasizing this all the time. First, Q and K share exact the same format in the mathematical expression, but Q indicates current concentration and K is the final or equilibrium concentration. When you compare Q and K, you can judge to which direction the reaction will be shifting to if Q is not already the same as K. So next, we are going to shift to a different topic. Previously, we talked about generically how to mathematically express the K. We do know you have the ratio of the products over that of the reactants raised to the corresponding chemical coefficients. All right, let's look at this example. In this example, what is different? The difference is in the second example, all right, as you see over here. You have a solid state, then you have gas state. You have different states. For this kind of situation, we call them heterogeneous equilibria, which means you have different phases over here. So let's look at how we will express this the equilibrium constants mathematically. As you can see, for the law of mass action, if we do exactly the same thing, you would have some equations like this. But do notice the concentrations for the solid state, okay, they are constants. Why? Because concentrations are related to the corresponding densities, right? The density for the solid is exactly the same. So for a certain amount of this material, or any amount of this material, the concentrations, which is the number of moles divided by the corresponding volume, will be exact the same, no matter how much material you have over here. So the concentrations for solid state, I'm going to write this over here, concentrations for solid state, or actually for liquid states the same, liquid states are constants for all substances. Okay, so basically what this tells you is, hey, that's a constant already, that's a constant already. So if you rewrite it, this ratio, top over bottom, that's another constant. All right, so if you divide the left side and right side, so let's do a K prime divided by K prime, and you name this new thing as Kc prime, then you would have Kc prime equals the concentration of CO2. And that's exactly what we are asking you to do when you try to mathematically express the equilibrium constants. Do not include any solid state, pure solid state, or pure liquid state. All right, so in the Q or K expression, okay, do not include pure solid or liquid. That's it. Okay, all right, so let's look at this for one more time. For this particular reaction, you have two solid states over here. So if you want to do the K, you don't have to write K prime over here because we know the whole procedure already. So the Kc would be written as the solid state excluded with gas phase, or if you have aqueous phase. Do remember aqueous is different from liquid phase. Okay, aqueous means you have something dissolved in it, you have different concentrations, but you have water listed as a liquid, that's as a solvent. The concentration of water, liquid, or solid, that means ice, okay, will be always the same, no matter how much you have. But in the previous example, I'm going to emphasize one thing. Hey, did you notice that? We do include water. Why? Because here, water is in gas phase. If it's in liquid phase, for the K expression, we will not include it. I hope you notice that difference. That's why you have noticed I emphasize, please include the phases for all the reactants and products. And that's why. Because when we write the heterogeneous equilibria constants, we do not include the pure solid or the pure liquid. Next, we are going to talk about if a reaction at equilibrium is perturbed by the change of certain conditions, to which direction the reaction will shift to if it does this. So, the Châtelier's principle just tells us how the reaction will be reacting if such a perturbation is applied to a reaction at equilibrium. Basically, Le Châtelier's principle tells you a system at equilibrium will respond to a stress, also called a change of condition, right, in such a way that it releases that stress. For example, if you add a concentration for a certain substance, then the reaction will shift to the direction that will make that concentration a little bit less. All right, so let's look at an example. For example, if you remove CO2, all right, you remove CO2 over here, so you have a less CO2. Hey, remember, the reaction is at equilibrium to begin with. If you remove CO2, now you have a less CO2 than you need at equilibrium. So to re-establish equilibrium, the reaction will shift to the right side. But you can also analyze it by comparing Q to K, because if you remove the products, that means your Q, which includes the current concentration with less CO2, Q will be smaller than K. So this also tells you the reaction shift to the right side. But what Le Châtelier's principle tells you is we don't have to do this analysis. And we simply know Le Châtelier's principle tells you, hey, if you add one thing, I'm going to shift to the direction that will make this change to a lesser degree. Okay? But I want to let you know the real reason behind the Le Châtelier's principle is because the change of condition has caused either Q and or K change. So the Q and K are not the same anymore. If they are still the same, then the reaction will not shift because it will be still at equilibrium. So with this in your mind, you will not make the simple mistakes. Okay, let's look at some examples so you know what I mean. All right, but we are not going to keep just analyzing the details. Okay, so first we talked about the change of concentration. So if you remove the products, okay, the reaction will shift to the product direction. What if I remove H2O? If you remove H2O, you will have less reactants. The reaction will shift to the left side. If you add H2O, H2O what? In gas phase, okay, I want to emphasize that if it's H2O liquid, the concentration will be a constant to begin with. It will not change the Q or K. All right? Okay? All right. So let's look at the, here we have changed the reactants or products. All right. So next, what about you change the volume? Or you compress if you make the whole container smaller. All right. So you compress the whole reaction. Or you expand the container. What's going to happen? So what's going to happen is you can, if you're interested, you can look at how they analyze this. Okay. The key idea is after the change, Q and the K, if they are not the same anymore, then you can use the Q and the K comparison. Still remember, if Q ended up greater than K, the reaction will shift to the left side. Q smaller than K, after the perturbation, the reaction will shift to the left. Q equal to K, no shifting. So if you're interested, you can look at the detailed analysis. But I'm just going to summarize this. All right. So if you change the volume, or in another word, you can compress the container or expand the container. All right. So if you expand the container, the reaction is going to shift to the side that has more gas moles. What do you mean? Because if you expand it, right, it becomes more diluted. Okay, so the pressure actually decreases. So the Châtelier's principle tells you, hey, you got to increase pressure. How to increase pressure? You increase gas moles. So expand. So if you expand the container, so the reaction will shift to the side with more gas moles. Okay, what about compressing? Compressing would be opposite, right? So if you compress the container, the reaction will shift to the side with less gas moles. Okay, so if for example, if you decrease the volume, okay, what do you mean decrease? That means compress, right? Decrease the volume. All right, that means the whole pressure is gonna be increased for the system. So you're gonna move to the side that will decrease the total pressure. That means move to the side with less gas moles. In this case, you have 2 on the left side, you have 1 moles of gas on the right side. So if you compress the container, you will shift to the side with less gas moles, which is right side. Okay. And the bottom just tells you, you can actually do detailed analysis by comparing the new Q with the K. All right. So, but we don't have to. But if you're interested, you can look at this whole procedure, which is listed over here. Okay. All right. Look at another example. So let's just do this. If you're going to expand the container, that's the original equilibrium established already. Okay. Now expand it. Which direction will this shift to? Expand it, you will shift to the side with more gas moles. The left side has 1 plus 3, 4 gas moles. That's why you shift to the left side. If you compress it, you're going to shift to the side with less gas moles, which means you shift to the right side, because the right side you have 2, left side is 1 plus 3, which is 4. Okay, is it quite straightforward? But again, emphasize one thing. The only reason Le Châtelier's principle is applicable is only if this perturbation will cause the Q and or K change, causing Q and K to be not equal, or else Le Châtelier's principle cannot be applied. That's the caveat for Le Châtelier's principle. But we're going to go over those examples. All right, okay? All right, let's look at another example. I'm going to simply write another example. For example, you might have, let's do CO reacting with H2O. Gas phase gives you an equilibrium. That's CO2, gas phase, and H2. All right. So here's the question. For this reaction at equilibrium, which means it's already at equilibrium, all right? If we compress the container, to which direction will the reaction shift? So we're going to say we're going to compress the container. So to which direction the reaction will shift to? Hey, remember, when you compress it over here, the left side and the right side, left side has a 2 gas moles, 1 plus 1. Right side is 1 plus 1 as well. Hey, so you have exactly the same number of gas moles. So the reaction will not be shifting at all. If you compress it, no shifting. If you expand the container, no shifting either. All right, let's look at another example, which is kind of confusing for some students. All right, look at this example. So we have a CO reacting with Fe2O3. All right, okay. So then this becomes CO2 gas phase plus FeO. So let's balance this reaction a little bit, okay? All right, so we're going to balance this. This is 2. That's it. The reaction is balanced over here with 4 oxygens on the right side, 4 on the left, 2 iron on the left and right, and 1 carbon on the left and right. So it's balanced already. For this reaction, let's do the same thing for the compressing or the expanding of the container. So what's going to happen? Hey, look at that. This guy, FeO3, that's actually the rust, okay? That's iron 3 oxide. That's inside of the phase. And FeO, or iron 2 oxide, that's also inside of the phase. So if I compress it or you expand it, it doesn't matter. Why? Oh, you might be thinking, oh yeah, over here it's this is 1 plus 1. On the left side you have 2. On the right side you have a 1 plus 2. No! We are talking about the gas moles, folks. For the solid state, it doesn't even matter. Why? Because they don't cause the change of the pressure. The real reason behind the Châtelier's principle is any change will cause either Q and or K to change. So Q and K are not equal anymore. That's why you shift. Over here, it's the same number of gas moles on the left and right. Did you see? So either you compress it or expand it. No shifting, no effect. All right, okay. Let's do another thing. What if? What's the effect of, let me say, add some Fe2O3? Will this reaction shift or not? Oh, some students might be confused. Oh yeah, you have more reactants, so the reaction is going to shift to the right side. Hey, remember, remember, you add a solid state over here. A solid has a constant concentration to begin with. So no matter how much material you have inside, that concentration term is a constant. So this will not change the magnitude of either Q or K. And in other words, although in this case you add more more reactants, no shifting because Q and the K will stay the same. Why? Because this solid is not even included in the either Q or K expression. Or in other words, the constants for these pure solids or liquids, they don't change depending on the amount of material you have. So that's why, in this case, no matter how many solids you add in, the reaction will not shift. Okay, hopefully this clarifies some of the confusions you might run into. All right, okay, next we're going to talk about the temperature effect. So for example, the same reaction we're talking about, reaction is exothermic for this reaction. Why? Because it's a negative sign over here. So for any temperature effect, I strongly suggest you write the exo in the form of heat on the product side, because you release heat as the product, just like that way, okay? It's easier. But the real reason is because changing temperature will change the K. Q will not change because the concentrations have not changed at that moment. But K will change. This is quite important, okay? So K will depend on temperature. Actually, in chapter 18, we'll go into the details about how K depends on temperature, okay? All right. So if you increase the temperature, that means you increase heat. The reaction will shift to the other side, to the side that does not have heat, okay? Because why? You add more heat. That means you just treat heat as if it's one of the reactants or products. So you add more heat. I'm gonna move to a different direction of that heat side. You see? So you add heat. You heat up the system. You're gonna shift to the left side. So if you heat or increase the temperature, so it's like you add the heat, so the reaction will shift to the left. What if I cool down the system? That means it's the same as take away the heat. I have less heat now, I'm going to move to the right side, okay? All right, so just to treat heat as either the reactant means it's going to be endothermic, right? So you absorb heat. Exothermic, just add the heat to the product side. Then you will do the shifting comparison. Okay, that's how you do it. This reaction temperature effect for these reactions can actually be observed if the reactants and products carry different color. As you can see in this example, for lower temperature, okay, it carries a pink color. Okay, all right. So higher temperature, it carries a blue color. Okay, why is that? Can you tell me if this reaction is exothermic or endothermic? How do we know? Hey, let's say this reaction is endothermic. If it's endothermic, see if you will see this phenomenon, which means when you increase the temperature from 5 degrees to 75 degrees, will this shift to the right side, which is blue, right? Okay. If it's true, that means it's endothermic, or else it's exothermic. So if you have heat, I add more heat to this. Oh, you shift to the right side. Why? Because you have more reactants now. Okay? As if you have more reactants. So you shift to the right side. Oh, you become more blue. That's exactly what you expect. So this reaction is endothermic. Okay? All right. Let's summarize what we have learned so far. If you have gas system, do remember, if you have pure solid or liquid, you do not consider pure solid or liquid. Or if you add some pure solid or take away some pure solid or liquid, it's not going to affect the equilibrium at all because they are not part of the Q or K expression. Okay, although here it gives you gas phases, but you do need to keep that in your mind because it's very often tested. So in this case, you add more products or take away, add more reactants or take away reactants or products or whatever, or you change the volume by compressing or expand the container, or you can change the temperature, okay? We have talked about these situations. Now let's talk about another situation, which is I'm going to add some catalyst to the system. How is this going to change? Hey, remember, folks, when you have initial state in the catalysis, the uncatalyzed reaction has higher activation energy. Okay, the catalyst changes route, but it does not change the initial and the final, which means the reactants and products are exactly the same, right? You see what I mean? So the equilibrium constant only depends on the initial and the final. If you don't change the initial or final, the K will not change. The Q, since you add a catalyst, which is not any part of the Q or K expression, so no shifting. The reaction will not shift. If you add a Q, the reaction will become faster in both directions, in the forward and reverse directions. But the reaction will not shift. Okay, All right. So similarly, if I add an inert gas into the system, for example, let me just give you the same example we've been talking about. Okay. So this is let's do NO2 gas phase, and you have this N2O4. All right. So if you add some helium into the system, so how will the reaction shift in? How will the reaction be shifting? No change. Why? Hey, remember, Le Chatelier's principle is only applicable when that perturbation changes either Q and or K. Helium is not even reacting with any of these things. It's not part of the Q or K expression. Or in other words, after you add helium to it, the Q or K will not change. Neither Q nor K will change. So Q and K will stay the same. No effect, no shifting. All right? Okay, so if you add a catalyst or you add an inert gas into the system, no shifting. All right? So that's it about the Châtelier's principle. Now let's talk about the next thing, which is the calculations based on equilibrium constant. For the calculations, usually when you look at different textbook, they write this differently. Sometimes you say so-called a Rice table. That means it's for the reaction for the initial concentration, for the change of concentration, for equilibrium concentration. So it's called a reaction ice table, or for many other textbooks, we simply call that ice table, which means it includes the initial, change, and equilibrium. Okay? All right. So let's look at one example, how you set up so-called a Rice table or ice table. You give a reaction between H2 and I2. So a hydrogen reacting with iodine gives you 2 moles of HI. All right, hydrogen iodide gas. So initially you have concentrations like this with no products. So how do you set the Rice table or ice table? So basically, let me write this down. This is the initial concentration or partial pressure. In this case, it's partial pressure. Okay, all right. That's the initial concentration as provided. Right. So now if you want to find out the final partial pressures or concentrations, what are you going to do? You're going to assume the change, because you don't know the change. You don't have the final concentrations, right? So you have to assume the change to be a certain number. We do know the reaction will be shifting to the right side because you have no products, right? So that's why you have a negative x over here, negative x over here. But this guy, don't write negative plus x. Why plus first? Plus because you have products, it's going to increase in concentration or partial pressure. But do remember chemical coefficients. You have 1 before H2, 1 before I2. You have 2 before HI, which means for every H2 or I2 that is consumed, you can generate twice as much. You're going to generate twice as much HI. That's why you should have put a 2 over here. All right? So that's why you see exactly the same thing as I just talked about. Now, what's the final concentration? Final concentration is also so-called equilibrium concentration, because all reactions will reach equilibrium state in the end. All right. So you do add the initial and change, you get the final concentrations over here. That's how you set up so-called a Rice table or ice table. If you are given the K, that's the concentrations or partial pressures you use, because the equilibrium constant is based on final or equilibrium concentration or partial pressures. So in this case, when you write a Kp expression, it's the final or equilibrium partial pressures over here in this case. So it's 2x, the whole thing raised to is 2x raised to 2. If some students write it this way, that's totally wrong. It's the whole thing 2x, which is over here. Okay, you see that 2x over here? All right. It's raised to 2. That's the 2. That's why you raised to 2. Okay, divided by partial pressure of this and the partial pressure of that. So you write this out. Now you can solve for k. All right. So after you do the solve for the quadratic equation, you find out that x has two possible numbers. Are they both correct? Or which one is correct? So basically, you do know one thing. Let's go back to that so-called rise table. Hey, we know the reaction is going to shift to the right. That's why you minus a number. So first thing, this x, after you solve it, I'm going to analyze to you, okay? This x must be greater than 0, right? That's the first thing. But both of these are greater than 0, so which one is correct? Hey, another thing when you go back is, hey, if I have an x over here, minus certain x, okay? You cannot consume more than you have. Or in other words, this x you see over here, this x, in this case, must be smaller than 1.00, must be smaller than the initial. Similarly, for the second one, it must be smaller than the initial. So x must be smaller than 1.00. For the second one, x must be smaller than 1.03. So that's why when you have two solutions over here, this one is correct. The other one, 1.415, it's greater than your initial, folks. You cannot consume more than you have to begin with. So that's why you have x equals 0.791. But that's not the final answer, because we are asking you to find the final partial pressures for these reactants and products. So that's the final, okay? It's 1 minus x. Okay, go back to the ice table or rise table. So look at that. See, that's the final. Hey, over here, too many circles over here. You see that? Okay, that's the final. That's the final. That's the final. That's why you have what you have over here. You see that? Okay, everything. That's the final answer. Okay, so hopefully you do understand everything we just talked about. For this next example, actually some information is missing. Let me add it over here. All right. So basically, this tells you initial concentrations, or initially we have the partial pressure Pn2 is 0.79 atm, and we also know PO2 initially is 0.21 atm, and then you have no nitrogen monoxide, no nitrogen monoxide to begin with. Okay, so we also tell you the Kp is 1.00 times 10 raised to -5. So we ask to find equilibrium concentrations. Okay, so that's the whole question. Sorry about for the missing information. All right. So basically, to begin with, you put down the initial concentrations. Because you have no products, the reaction must shift to the right side. So you do minus x because you have a 1 before N2, 1 before O2. And you put a plus 2x over here because you have a 2 before that. All right. So you do the Kp expression using the final or equilibrium concentration. So you write this. Do remember, because Kp is small. So I'm going to add this over here. That's the Kp is small, which means the reaction barely moves at all, right? So x is very small compared, so x is very small compared to the initial concentration. X is very small compared to initial concentration. That's what that means, okay? Because K is small, reaction barely moves, it lies to the far left. The change of concentration is really small. So for this reason, x compared to the original is the same as 0.79. So because x is small compared to 0.1, so this is the same as that. Did you see? That's why you write it this way. You cross out that x, but not the top. You don't cross out the 2x, because 2x is compared to the original 0. No matter how small x is, it's still much, much greater than 0, isn't it? Right? Okay, so when you do this calculation, you will be able to easily figure out what x is. Then you can calculate, for example, if I want to ask you, what is the final, let's find the equilibrium concentration for NO, okay? So what is that? Hey, you don't stop over here. The NO equilibrium concentration would be, hey, look at that, that's NO equilibrium concentration. That's my NO equilibrium concentration. So this will be NO EQ would be 2x, okay? It would be 2 times 6.44 times 10 raised to negative 4. This would be 1.28 times 10 raised to negative 3 molar. That would be your final answer. Okay. All right. Let's do maybe one more example we have over here. In this case, we tell you the initial concentration the same way, and it gives you the K, and that we tell you the initial concentration, we give you the K. How do you do this problem? You use the rise table and make the change certain number of x's. Then you solve for x. That's exactly how you do it. Okay? You see that? That's how you do it. Are we gonna? This is the next is what you see over here. Okay, solve for this. You set up the ice table. Initially, no products. So here it's minus 2x because it's a product. It's a reactance. It's going to be shifting to rise up because we have no products to begin with. So after that, you have 2x plus x because you have a 1, so that's why it's plus x and plus x over there. So you have the equilibrium concentrations as you see over here, and then you write the K. So K is written as you see over here. All right, now you have to solve for quadratic. After you solve for quadratic, do remember, I can rewrite this thing, right? So if you rewrite this thing, it would be, actually some students will get this wrong, okay? X over 0, because you have the same exponents over here. So it's 0.1 minus 2x squared is 0.11. Hey, do remember, so this just gives you x over 0.1 minus 2x. This will be, this thing will be plus or minus square root of 0.11. You see that? Okay. Hey, why is that? Let's say, you know, for example, if I have x squared equals 9, right? I mean, if. Okay, what is x? X actually equals plus or minus 3. You see that? Not just the 3. Okay, so mathematically, you got to know it's a plus or minus over here. So for this reason, when you try to solve for this quadratic, because you have a perfect square over there, so it's the plus, this is plus this 0.11. That's the square root of 0.11. That's this number and the negative 1. You solve for both x's, and you have two numbers over there. So which one is correct? As we analyzed in previous example, we do know first x must be greater than 0, and the second thing, your change of concentration cannot be greater than the initial. Hey, if you have x equals the -1, hey, that's wrong. So that's why the first one is correct. Okay, then you can calculate the final concentration as you see over here. All right, so that's about it. And that's all you need to know about how to do the calculations based on equilibrium constant using so-called Rice table or ice table. Let's summarize everything for this type of calculation. Basically, if you are given only if you are given initial concentrations and the K and the equilibrium constant is either Kc or Kp, all right? So what you're going to do is you build ice table, or if you prefer, you can call that a Rice table. Okay, then solve for x. You can find the final concentration or equilibrium concentration. In this process, trying to solve for x, sometimes you have to solve for the quadratic equation. But if k is extremely small, you can actually do so-called small x approximation. What is small x approximation? We actually talked about it. So for example, over here, because k is small, so you cross out the change. See? So let me put this down. So this is so-called a small x approximation. If k is small, use small x approximation, which means you neglect the change of concentration compared to the initial ones, then you will be able to solve for x more easily. So that's it about this lecture. Hope this helps, and have a good day. Bye-bye.